Welcome to these videos on the different metrics of photovoltaics. In the previous videos we discussed the historical and recent developments in the field of photovoltaics. Much of these historical efforts were devoted to the improvements in the conversion efficiency of PV devices. The development of the record conversion efficiencies over time are recorded in the Best Research Cell Efficiencies chart of the US-based National Renewable Energy Laboratory, or NREL for short. Crystalline silicon, the dominant PV technology and the workhorse of the PV industry, has seen some amazing progress in recent decades. The crystalline silicon device efficiencies for different crystalline wafer types and different device architectures are recorded separately in the NREL chart. The record efficiency of crystalline silicon has increased from about 14% in 1975 to a current record of 26.7% of Kaneka for an advanced crystalline silicon solar cell without light concentration. Meanwhile, alternative families of PV technologies have progressed as well. The efficiency of several thin film technologies has increased steadily over the last couple of decades. The performance of CIGS and cadmium telluride solar cells is very similar, with record efficiencies in the 22 to 24% range. The performance of thin film silicon solar cells is lower, with a stabilized record efficiency of around 14%. Of all the different PV technologies, the III-V technology results in the highest conversion efficiencies of over 47% for cells under light concentration. Another field of PV that has developed quickly in the last decade are the perovskites, for which efficiencies of close to 26% have been achieved. Note that the working principles, advantages and limitations of the different PV technologies are the topic of the second course in this series. The fact that the PV technology with the highest conversion efficiency, so with the capacity to generate the highest power density, does not dominate the PV market, already indicates that there are more metrics to PV besides the photovoltaic conversion efficiency. In this set of videos we will introduce you to a number of very important metrics for PV. An obvious metric for PV is the cost effectiveness of different PV technologies and different module designs. Simply put, if a PV module based on a certain technology is twice as efficient but 4 times as expensive to produce, it will not be as cost effective. In this visual, the price per watt peak of different PV technologies are compared. Note that with current PV developments these numbers change relatively quickly. Nevertheless, we can understand from the figure why the market share of the III-V PV technology is limited. Despite the higher conversion efficiencies, the price per watt peak is about 400 times higher than that of crystalline silicon and cadmium telluride, due to much more expensive processing. There are certain market niches, however, such as space application and concentrated PV, where generated power density is the most relevant metric, and III-Vs are therefore the best available option in these market niches. We'll discuss these applications in more detail in the second course of the solar energy program. It is important to note that the rated power of a PV module is measured on the standard test conditions. The cost effectiveness of a PV system depends on the energy yield under real-world conditions. The cost effectiveness will therefore depend on the location where the PV system is installed. The available solar radiance at that location will strongly influence the energy yield. There are other important PV metrics that influence the energy yield. These include the temperature coefficient and the shading tolerance of PV modules. In this solar energy program you will learn that the energy yield of a PV module generally decreases with both an increasing module temperature and when part of the PV module is shaded. The influence of temperature and partial shading on the energy yield of a module depends both on the PV technology used for the cells in the module as well as the design of the module. In this visual, the attractiveness of different PV technologies for different locations in terms of the temperature coefficient and shading tolerability is assessed. PV materials should preferably have low temperature coefficients and a high shading tolerability. The visual shows that the low temperature coefficient of amorphous silicon solar cells make it a very attractive option for hot and sunny or partly cloudy locations, while the high shading tolerability of CIGS make it very attractive for cloudy locations. The spread in the colored clusters, so for different tested modules based on the same technology, predominantly indicate the influence of the module architecture. We will investigate the influence of module architectures on the energy yield in some more detail on the third course of the solar energy program. This ends our first video on the different metrics of PV energy conversion. We will continue our discussion of the metrics in the next video.